Hi, I'm Alex. I'm a robotics researcher at ETH, and in this video I'm going to present our paper on robot motion planning. So let's dive right in. Alright, so the paper that I'm going to be talking about today was published in the Robotics and Automation Letters and relates to gait and trajectory optimization for legged robots. So why are we even concerned with legged systems? What are the advantages of legged systems compared to rolling or flying vehicles? Well, one of the big advantages is that legged systems do not need a continuous path to move from a start to a goal position, but discrete foothold positions are enough to traverse terrain. And this allows motions such as these, which would be unthinkable with a rolling vehicle. Furthermore, legged machines move by creating contact with the environment, and these contact forces that move the robot forward can be quite large, which allows a legged system to carry such heavy payload. So the question now becomes, how do we make a legged machine perform these types of actions? We have a high-level task, which is a specific robot. The kinematic and dynamic model of a robot should reach a specific goal state. It should climb stairs. It should do something useful in a pre-specified environment. That's our high-level task description of what we want. And on the lowest level, we have to somehow transform this into actuator commands, so force or torque commands, that we can send to the hardware to perform this motion. And now, what we try to do is we try to separate this into some solvable subproblems. So one thing that's very often done in robotics is a desired motion plan is generated first. So a desired motion plan is a sequence of states that we want the robot to execute. And these are then given as a reference to a tracking controller, which takes these as a reference, reads in the sensor data, and then produces the appropriate torques at every point in time in order to track this reference. So this already decouples the motion plan that we can generate here from the task of correct control loop design, which is done below here. So the question now becomes, how do we go from this high-level task to a desired motion plan? And this is what we consider motion planning. And it is a difficult task because this high-level task here proposes a lot of restrictions, and hand designing a motion that fulfills the kinematic and dynamic restrictions of the robot, it reaches the goal state and at the same time makes sure that the environmental contacts are always fulfilled, is quite difficult to hand design. So what's often done in this case is that this is again separated into distinct subproblems. Instead of going directly to a desired motion plan, it's possible to reformulate this high-level task description in form of a mathematical optimization problem. So we formulate this task as with some equality and inequality constraints, and then there exists already off-the-shelf software, nonlinear programming solvers such as IPOpt and SNOPT that are specifically designed to solve such a mathematical optimization problem and then produce, by solving that, the desired motion plan. So in a way, we're outsourcing this complexity that we would have in hand designing and keeping all these different connected elements in our head, outsourcing this complexity to off-the-shelf software. So what's left that we have to do is we have to somehow translate or transcribe this high-level task into a set of mathematical equations. And this is in literature called a direct method, and specifically, for instance, collocation. And this is what we're going to be talking about in this paper. The goal of this work is to find a minimal mathematical representation for only the most important elements of legged locomotion. We want to have as little tuning parameters as possible, because the correct values for these might be task dependent or require expert knowledge to specifically tune. So our goal is to find one general formulation that works for all situations. To achieve this, we don't include a cost function, which often requires careful tuning of the weighting parameters to trade off between different objectives. Instead, we model the legged locomotion problem purely through constraints that have to be satisfied to create physically feasible motions. So strictly speaking, we are formulating a mathematical feasibility problem And the entire rest of this talk will discuss those equality and inequality constraints. So before diving directly into the formulations that we used in our paper, I want to have a brief look at how the solver actually finds those specific motion plans on a bit of a higher abstract level. So this is the space of all possible motion plans that exist, a sequence of states and inputs. And this space of motion plans is restricted by those motion plans that actually reach our specified goal state. So this already restricts the motion plan to a specific area. Furthermore, we have a model of our robot. We said we have a kinematic and dynamic model of the robot. We have joint limits, we have actuator limits, and this furthermore restricts the space of all feasible motion plans. And finally, we're operating in a specific environment. We might have stairs, we have gaps, we have specific places where we can place our feet. And also this restricts the space of feasible motion plans further that comply with all the constraints that come with the environment. And what's left at the intersection of all these restrictions, these are those motion plans that actually fulfill all the constraints and will generate are actually feasible motion plans that we can then send to a low-level tracking controller and hope to execute on a physical system. This is the area that we want to actually find when we're solving an optimization problem. Now let's look at this optimization problem that we have. Now what's often done is that the motion plan generation is decoupled into different steps, and each of these steps specifies a few elements of the entire motion plan in advance. So a very traditional way of performing this motion planning is first you have a footstep planner that predefines at which places the feet should be placed, in which order the feet should be placed. The same goes when we're using the linear inverted pendulum. What we fix in advance is we fix the center of mass height and the body orientation, for instance, because these are all assumptions that you have to make beforehand to use this inverted pendulum. Now, this makes sense because it reduces the complexity of the problem. So if we look at that in terms of this graph here on the right, what this does is it restricts the search space to this highlighted area here. So we are not searching over the space of all possible motion plans, but we're only searching over the space of all the motion plans with the elements here on the left fixed in advance. And this can help the solver more reliably find a solution. It can speed up the search because the optimization algorithm doesn't have to search over the entire space. So there's some benefits to this. However, what we have to keep in mind is that we do not know in advance where this green feasible area is of motion plans that fulfill all our constraints. That's the whole reason why we're using optimization. So if we restrict the search space to an area like this that encompasses the green area, that's totally fine. But what could happen as well is that we actually restrict the search space to an area like this. This is where the solver is going to look for solutions, and it does not even intersect with the feasible area. And especially for more complicated motions, for more complicated terrain, it becomes harder and harder to have an intuition where this space of all motion plans actually lies, and we can be less and less confident that restrictions that we made in advance encompass our area like this. So one way to sort of increase the chances of finding a feasible motion plan is just to try to open this search space up as much as possible. So try to give the solver as much freedom as possible to tune as many elements in order to reach that green feasible area. And this is what we call integrated motion planning. So fixing as little elements as possible in advance. And that's the motivation for our work in order to increase the likelihood of finding a feasible solution to all the constraints. In our formulation and the paper that we're presenting today, we are optimizing over the three-dimensional center of mass motion. We optimize over the base orientation as well. We don't fix this in advance. And we optimize over the three-dimensional foothold positions, as well as, instead of, for instance, the center of pressure or the ZMP, we optimize directly over the three-dimensional forces at each foot. So these are all these optimization variables that the solver can modify in order to try to fulfill the imposed constraints and find a solution to our problem. So one of the main constraints that we have to enforce is that the motion complies to the physics of our legged system. So we model the robot as a single rigid body with a specific mass of the robot and a 3x3 inertia matrix. And depending on how the feet forces and feet positions are, this has an effect on this single rigid body according to these equations. So these are the linear equations, the three linear equations that dictate how forces affect the center of mass, or the center of mass acceleration. And these are the angular equations that dictate the angular center of mass, base accelerations. We make a few assumptions in order to use these equations. And one of the assumptions is that we say that the motion of the legs does not significantly influence the motion of the base. So the robot has light legs, and even if the robot swings these legs very fast, it does not cause a significant acceleration of the base. And what this allows us to do, it allows us to formulate this equation fully in Cartesian space. So we have no dependency on the joint angles and the nonlinearities that are introduced with it. When we look at now how these produced motion plans look, at every point in this trajectory, we're enforcing the above equations as equality constraints in our optimization problem. So while the optimization algorithm is choosing the foothold positions and the forces, at the same time it's making sure that the base motion that it's choosing complies to these above equations. So another important constraint that we have to enforce in order to create physically feasible motions is the kinematic model. So the kinematic model is an approximation of the joint limits and makes sure that we do not violate the joint limits. We formulate this by saying that while the optimization algorithm is changing the base position and orientation, as well as the foothold positions, foothold 1 and foothold 2 in X, Y, Z, at every point in time it has to make sure that the foothold positions are inside the blue boxes that move relative to the base position and orientation. If the feet are inside these blue boxes, then this is sort of an approximation that the joint limits of the legs are not violated. So this is a very rough approximation, but keeps everything in Cartesian space and nicely to formulate. So here you can see a bit how this motion plan looks while the base is moving now. While the optimization is moving the base up and down, these blue boxes move up and down relative to the base as well. And the algorithm has to make sure that the footholds, the blue dots, stay inside these blue boxes at all points in time in order to not violate the joint limits. So now that we determined how to represent the dynamic and the kinematic model of the robot in terms of mathematical equations, next we want to talk about gait optimization. So we do not want to pre-specify the gait in advance, because according to this initial motivation that we gave, we want to try to keep the search space as open as possible in order to increase the chances for our solver to find this green area, this feasible area. And this includes also not restricting the gait in advance, because restricting the gait in advance predefines in what order, for instance, external forces can be applied that affect the base motion. And additionally, sometimes it can actually be quite difficult to know in advance what is the best gait sequence to cross irregular terrain with a quadruped robot, for instance. So the best is if we could outsource this complexity as well to the optimization algorithm, to the solver, and let it pick the best sequence for a specific task. So if we look at, for instance, a sequence for a biped robot here, we have a sequence with a right leg in contact, a double support phase, a left leg in contact, right leg in contact, and again double support phase. And this sequence is defined by integer variables. So these are not continuous variables, but each phase here, right, double support, left, are integer variables. And this makes it very difficult to optimize over them because they don't change continuously. And integer programming can be used in order to find a correct sequence here, but it can also lead to a combinatorial explosion if there's many more different phases, for instance, for a quadruped robot. So we want to try to avoid this and optimize over this in a different way. Now, let's try to break this sequence that we have here down and look at each leg individually. So here we see the left and the right leg. We see a pattern here. If we look at the left leg, for instance, we see that the left leg alternates between a swing phase, a stance phase, swing phase, and a stance phase. And the same for the right leg. And this is independent of which gait sequence we have here for the combined robot. Imagine for a single-legged hopper, for instance, the hopper will always alternate between swing and stance and swing and stance. So for hopper, there will be no need for gait optimization. Now, how can we use this concept also for a biped robot? What actually varies between different gaits in a biped robot? Well, if we change here, for instance, the duration of the right leg's swing and stance phases, as you can see here, and now we look at the complete robot gait sequence again, what we see here is that a flight phase emerged that we didn't have in the original sequence. And this flight phase emerged not by changing the integer variables in any way, but simply by changing the continuous durations of each individual leg's swing and stance phase. So what this means is that a gait does not have to be defined through integer variables, but a gait can be fully defined by the continuous phase durations of each individual leg, swing and stance phases. And this is great news because these continuous variables, delta t, are variables that we can throw into our nonlinear programming solver because they are continuous. This is the high-level idea, what we're going to be using in order to allow our optimization algorithm to determine the best gait for our task. So how can we now use this information to formulate some of the constraints that are present in legged locomotion? So let's look at some of the constraints related to environmental contact and try to find a formulation for these. If we look now at one individual leg, and we look at a trajectory for the position and force over time that we see here in blue and in red. From the previous analysis, we now know that each individual foot will alternate between swing and stance. So a swing phase here in white, stance phase, swing phase, stance phase. This we know. So we can incorporate this knowledge by saying that we represent each swing phase position, for instance here, by 3 polynomials, and each stance phase by another polynomial. And we know in advance already whether each polynomial belongs to a swing and a stance phase. So these 3 belong to a swing phase, and this one now belongs to a stance phase, and the same goes for the force polynomials. We know we'll represent this as a single polynomial, and we know this force polynomial will belong to a swing phase. This is without loss of generality. Now, we want to formulate some of these physical restrictions now, inherent to legged locomotion. So one of the main things is if we want to avoid slippage, the foot position cannot move while standing. Now, how do we formulate this in a mathematical way? The polynomial that represents the foot while standing, we already know in advance which polynomials represent a foot in stance phase. And we know that this polynomial then has to have 0 velocity. So what we can do is we can simply fix those polynomial coefficients that would cause a non-zero velocity before passing it to the optimization, and allow the solver, in essence, to only change, for instance here, the height of this linear polynomial, move it up and down. So no matter what the optimization algorithm chooses, this restriction is always fulfilled in advance because we don't allow the algorithm to modify those coefficients. And the same goes for the forces. So a physical restriction is that a force cannot exist while a leg is in the air. We again know which polynomials represent a force during the swing phase, and we can simply set those polynomial coefficients to 0 before passing it to the optimization algorithm and to the solver. So we don't even allow the solver to touch those coefficients to make sure that this constraint or this restriction is always fulfilled. And this is what we call phase-based end-effector parameterization. And the key here is parameterization because we enforce these constraints, these two constraints, before going into the optimization algorithm. So this is not any extra complexity that's added that could make the solver take more time. And we're using this previous information of the alternating swing stance phases in order to formulate it like this. And we don't, for instance, need complementary constraints that are often used in order to formulate these two restrictions. We showed how to enforce these two physical restrictions that we have, but there exists even more restrictions specifically related to the terrain and the environment that we're traversing. So let's see how we can actually formulate some of these terrain constraints in terms of mathematical equations. So what is the information that we're using from the terrain? So from the terrain, we need a height map. So we need to know at every position along the plane, and at every XY position, we need to know the height of the terrain. And we additionally want to know the slope. So we want to know the normals and tangents at every point along the terrain. And the terrain constraints are mostly active during the stance phases. So we're going to now have a specific look at some of the constraints active during this part of the trajectory in the stance phase, when a foothold is in contact with the environment. One of the very important constraints is that if a specific foothold is in stance phase, then the foot has to stand on the terrain. So the foothold Z position has to be equivalent to the height at the optimized foothold XY position. So what this means is that if this now represents the Z position of a specific polynomial, this has to be at the height, this height here has to be according to the height of the terrain. So a foot cannot stand in the air. A further constraint that's very inherent to legged locomotion is that forces can only push on the ground and not pull on it. This is also called unilateral constraints. What this means is that when walking and we're stepping on the ground, our feet cannot pull on the ground. And we can formulate this very naturally because we have all the variables required for this in our optimization algorithm. So we're optimizing over the three-dimensional forces. We project these forces onto the normal of the terrain. So depending on how the terrain is oriented, at the specific position wherever our foot, XY position, wherever our foot is standing right now. And we have to make sure that these forces that we projected here are greater than zero, so pushing and not pulling. So this is a very natural formulation, and it's equivalent to the formulation of keeping the center of pressure inside the support area, or the ZMP inside the support area. This is the same physical restriction that's modeled through these constraints, but here you can see a lot more directly how this relates to the physical laws. And finally, a further constraint that we have to enforce at every point in time is that the forces are inside the friction pyramid. The tangential forces have to be smaller than the friction coefficient times the normal forces, so the forces projected on the normal. So we have all the colored quantities here, the red and the blue. These are represented by polynomials that the optimization algorithm is tuning simultaneously. So here it can move the foothold positions around or the forces, and it has a lot of degrees of freedom in order to satisfy each of these equations. So let's see how this entire formulation looks in action. So what we're showing here are a variety of motion plans that are produced through our formulation and then basically generated through the NLP solver, off-the-shelf NLP software that generates these motion plans. And just as a summary, so we represent the robot as a single rigid body, as seen here, and the optimization algorithm is choosing the forces and foothold positions and body motions, and at every point in time makes sure that the single rigid body dynamics equation is fulfilled. The kinematic model is represented by these box constraints that say that while the optimization algorithm is moving the foothold positions, it has to make sure that they always are inside the blue boxes that move relative to the base in order to not violate joint limits. We do not fix the gait sequence in advance. So here the gait sequence is adapted over a few iterations in order to find the best gait to cross a gap. Here as well, the initialization still violates the physical laws, but as the solver proceeds, it finds a solution and a gait that can be used in order to traverse even such difficult terrain. In general, the terrain is represented by a height map and the terrain normals, so we can insert a variety of height maps into the terrain, and depending on, for instance, how the normals are oriented, this changes the friction cone, but the forces always stay inside the friction cone, even for such more complex motions. And even such very unintuitive motions come out of the optimization simply by defining a goal position for the robot to reach. Now, we don't define the gait in advance, and this can be quite difficult, especially for motions such as these, where it's very difficult to say what is the best gait in order to cross, but the optimization algorithm can figure this out with our formulation independently. Now, here we're showing that we can actually also track these motion plans that we produced in a physics-based simulator. So this is a type of verification that the constraints that we modeled in our optimization algorithm somehow capture the physics that are implemented in this in the gazebo simulator in this case. So it gives us a bit of confidence that we're modeling the correct thing if our motions can actually be tracked in simulation on a physical system. Now, this is still only a simulator, so the ultimate form of verification is seeing if these motions can also be tracked on a real physical system, because the physics in the world will be correct by definition. And as we can see here, even without using, we don't have any notion of a linear inverted pendulum, so we're planning directly over the contact forces and the body motion in 6-dimensional space, so the body is supposed to move up and down and sideways. We can still execute these types of motion on a physical system. So as a summary of what I talked about today, we presented a way to transcribe a high-level task description into a mathematical optimization problem that can then be solved with off-the-shelf software in order to produce motion plans that can then be tracked by a controller. And the characteristics of our transcription that we presented here, we're using a single rigid body dynamics model that abstracts the robot into one single rigid body and keeps the formulation fully in Cartesian space, independent of the joint angles. We try to keep the search space as open as possible by optimizing over the 6-dimensional base motion, the 3-dimensional foothold motions, and we do not fix the step sequence, the step timings, or the contact forces or the swing leg motion in advance, but allow the solver to determine all of these to best solve a given task. And this allows us to generate some complex motions on non-flat and inclined terrain included with flight phases for robots with a number of end effectors, 1, 2, or 4 legs. And through our phase-based parameterization, even though we're optimizing over the gait sequence, this can be done very efficiently. And for instance, for a 1-second horizon, 4-footstep quadruped motion, we can still solve this in about 100 milliseconds, which will in the future allow us to also use this in a MPC loop. I hope you enjoyed this presentation. These are some of the people that contributed significantly to this research. And all of the software that was used to generate these motions is open source. So Tower is the actual implementation of all the constraints that I've previously talked about. IFOPT is an interface to IPOPT and SNOPT. It's based on Eigen and allows to exploit the sparsity of eigenmatrices and allows easy formulation of all of these constraints, and the visualization and all of this is part of ROS. So if you're interested in using that. All right, I hope you enjoyed this presentation, and you can find the PDF, the software, as well as other useful links in the comment section.